So in section 7.3, we're going to use a method called a trigonometric substitution. So in the last section, we looked at trig integrals. So those were integrals that already involved trig functions, and we use u substitutions to simplify them. But here, our integrands, or our integrals, will involve expressions that look like square root of a squared minus x squared, root a squared plus x squared, or root x squared minus a squared. Or variations of those. And what we're going to do is we're going to use these trig substitutions to change these expressions into integrals involving trig functions that will simplify. So we're putting trig functions in instead of getting them out. Now, in the textbook, they suggest a substitution that goes with each one of these expression forms. But I'd just like to use the identity itself. So we know 1 minus sine squared is cosine squared, 1 plus tan squared is secant squared, and then secant squared minus 1 is tangent squared. So I just like to parallel the identity with the expression itself. So if you've got quantity squared minus x squared, that looks like 1 minus sine squared. So let's take a look at an example. I'll show you how this works. So we want to integrate x squared over root 9 minus x squared. So 9 is a perfect square. That looks like this expression, which corresponds to the trig identity 1 minus sine squared. So I'm going to write that underneath the integral here. Now we've got a 9 here instead of a 1, so I'm going to multiply through that trig identity by 9. So it's 9 times 1 minus sine squared. So if we multiply that in, we'll get 9 minus 9 sine squared theta. And so the 9 matches up, so that means that our x squared has to be 9 sine squared. So that's our substitution, is that x squared is 9 sine squared theta. And then if you take square roots on both sides, then x is 3 sine theta. And then the differential of x, dx, is equal to 3 cosine theta d theta. So now we'll start to change our integral over. So the x squared on the top, well, x squared is 9 sine squared. So this integral will be 9 sine squared in the numerator. And then in the denominator, we've got square root of 9 minus x squared, which is the same as 9 times 1 minus sine squared. So go ahead and put that in the square root. And then our dx out on the end here, 3 cosine theta d theta. So now we'll start simplifying here. So this will be integral in the numerator, 9 sine squared theta. Don't need the d theta there. We've got it out here. It's part of the dx. In the denominator, 1 minus sine squared is cosine squared. So this is root 9 cosine squared times 3 cosine theta d theta. And so this is integral 9 sine squared theta. And the denominator, square root of 9 is 3. Square root of cosine squared is cosine theta. And then we've got that 3 cosine theta d theta. And then the 3 cosine theta cancels. The 9 we can bring outside. So this is going to be equal to 9 integral of sine squared theta d theta. So we changed it into a trig integral. And then we know how to do trig integrals from the last section. So, and notice it's a trig integral, but no more square roots in here. And that's what was giving us trouble here, is because we couldn't just use the u substitution because we had x squared on top and not x. So remember what we do with all even powers of sine and cosine. There we will use the half angle identities. So this will be 9 and then integral 1/2 times 1 minus cosine 2 theta d theta. And that was this half angle identity again from the last section. And the 1/2 we can bring out in front. So we'll have a 9/2 out in front. And then antiderivative of 1 with respect to theta is theta. Antiderivative of cosine 2 theta is sine 2 theta. And then instead of multiplying by 2, the derivative of the inside, we divide. So 1/2 sine 2 theta. And then plus constant. And so we've done our antiderivative. So we got our indefinite integral here. However, it's in terms of theta. We got to put it back in terms of x's. So the way that you do that is you draw a right triangle here with your angle theta right here. And then you use your substitution right here. X is 3 sine theta. So x is 3 sine theta. So divide both sides by 3. So x over 3 is sine theta. And remember, sine theta is opposite over hypotenuse. So opposite of that, we're going to put x. Hypotenuse is 3. And then this side down here is going to be square root of hypotenuse squared minus the opposite squared. So this will be square root of 3 squared minus x squared, which is root 9 minus x squared. And that root 9 minus x squared should look familiar. It's right here. It's part of the integral. And that always happens. So when you use your triangle to change back, one of those sides should involve part of the integrand. So if sine theta is x over 3, then this theta is the angle whose sine is x over 3. So that's going to be inverse sine x over 3. So we got a 9/2 out in front. Our theta is inverse sine x over 3. And then sine 2 theta, well, we know what sine theta is. It's x over 3. We don't know what sine 2 theta is. But 1/2 sine 2 theta, if we go back to our half angle and double angle identities here, 1/2 sine 2 theta is sine x cosine x, or sine theta cosine theta if we're using theta. So this 1/2 sine 2 theta is just sine theta cosine theta. And we know what sine theta is. It's x over 3. So minus, that's this minus sine, got x over 3. And then cosine theta is adjacent over hypotenuse. So root 9 minus x squared over 3. Close up our parentheses, plus c, and we got it. So that is a trig substitution. So you match the identity to try and change it into a trig integral, and then use strategies from the last section. And then to change it back, you're using your right triangle along with your substitution. It's not u substitution, it's trig substitution. So with a u substitution, you go from x to u. With a trig substitution, you're going from x to theta.